Hey there, and welcome to my lesson on Taylor polynomials. This is piggybacking off of an introductory lesson that I have as a separate video for an introduction about where Taylor polynomials came from. It was kind of an exploration about how the Taylor polynomial idea came about. And what we're going to be focusing on in this video is how we can write Taylor polynomials for certain functions and how we can use Taylor polynomials to identify values at any given point of a particular value of derivative, like second derivative, third derivative, and so on. Taylor polynomials here, they're kind of giving us, whoops, didn't mean to move that around. Taylor polynomials are kind of giving us an idea of what we're going to be used for. The particular functions that we have in this lesson focus on those three. But it's telling you here, in fact, the tangent line approximation is going to be this as a first degree polynomial. Where here, where they're using a, whatever that a value. Now, our material seems to be focused, it seems to use c more than it does a, but other materials, whether it says c or a, it's referring to the same thing. In this case, this is what we would refer to as the center of the polynomial, meaning that's the value that we're kind of focusing in on to, approximate another function with. If the center of the polynomial that we're going to be looking at is 0, we would kind of look at that as what's known as a Maclaurin polynomial. But down at the bottom it says, now you know how to construct a Taylor polynomial. Again, that was kind of what the introduction to the Taylor polynomial was about in the previous lesson I'm referring to. But what is this? If you haven't seen it, it's not new in the world. It just kind of shows you how the Taylor polynomial came about. Now what we're going to be doing is we're going to take the rule that we established from that, and we're going to be utilizing it. And if you don't have it, it's no big deal. It's right here. So, and this is kind of what I was referring to on the previous page. If we're focusing here on the C's, maybe this was cut and paste from a different resource, why they're referring to f of a here in the introduction, but the definition of a Taylor polynomial here uses c. And a lot of the material that I have for this course does have c for it, so I'll just kind of keep with that. But the one thing that I want to include here, this right here, that number, that little subscript n, that refers to a degree. So I would read where it says p sub n of x, I would read that as a Taylor polynomial of degree whatever, degree n in this case. And in some cases, depending on the resources that you may be looking at, you may see it as p sub n comma a, or I guess in our case, we'll probably say c. And that was a terrible c. Of x like that. Okay, where in here, this n is still the degree, but the c that we have here, or a, depending on what you're calling it, that is illustrating what the center of the polynomial is going to be without having to tell you specifically in a problem somewhere. But this is what the Taylor polynomial series is. It's going to be something you need to make sure that you know. So we started off f of c plus f prime of c, and then it goes f double prime of c. And this right here does, technically it's over 1 factorial. Same thing here. This is technically over 0 factorial. But 1 factorial and 0 factorial both simplify to be 1, so we don't really bother writing them. We only start writing the factorials once we get to the second degree, third degree, fourth degree, fifth degree, etc. derivatives of f. Okay? And down at the bottom, what we see here, this is specifically what we would kind of be thinking about with a Maclaurin polynomial. And now Let's go ahead and take a look at an example. Let's use what we know about the Taylor polynomial to, in this case, suppose f is a function which has a continuous, it's differentiable, so that it's telling us that at 2 we have the function giving an output of 1, the first derivative gives an output of -3, 5, and -7 for the second and third derivatives. It's asking us to write a Taylor polynomial of degree 3 for function f centered at 2. Okay, so that's not a big deal. So the idea of the Taylor polynomial, one of the things that's going to make them work is that whatever the function is, the Taylor polynomial is going to be equal to that function at a particular at their particular values, meaning that if I were going to take the first derivative of this, it would be equal to the first derivative of the Taylor polynomial. And if we kept going, f to the nth derivative of x would be equal to the Taylor polynomial to the nth derivative of x. They would be equal to the same thing. That's essentially the foundation of what the Taylor polynomial series is. Taylor polynomial is going to be doing for us. So here, all I'm going to do is I'm just kind of writing out the general formula. I'm just writing out what the Taylor polynomial is. If you want to write it down in your notes, by all means, go for it. Otherwise, you don't need to, but I'm a big believer of anytime you're using a rule, you should kind of write it down, and so that's what I'm doing here. So we start off with f of c plus, then it goes to f prime of c times x minus c, and then it goes, so that would be first derivative, and so the derivatives represent the number of degrees that we're going to be having for our Taylor polynomial. So then we would get to f double prime of c over 2 factorial times x minus c quantity squared. So there's our second degree, and one more, we'll say f triple prime of c over 3 factorial times x minus c cubed. So that's the generic one, and because it's asking us to go to a third degree, this is as far as we need to go. So now we can start plugging in some values. So we're going to evaluate it at 2. So here I can say p third degree of 2 will be equal to, in this case, f, and I probably need to move that down a little bit. I don't think I'm giving myself enough space. Let's move that down a little bit, of 2 plus, and basically we're just going through and substituting 2 anywhere we have a c. Here I'm going to say f prime of 2 times x minus 2 to the first power plus the second derivative of 2 over 2 factorial times x minus 2 quantity squared plus the third derivative of function f at 2 over 3 factorial times x minus 2 quantity cubed. Now in this case, we don't really have to do a whole lot of work. We don't really have to try to figure out what the values are going to be from a polynomial itself. Okay, in this case, and that's one of the examples that we'll look at a little bit towards the end of the lesson. But in this case, they're kind of telling us what the values are going to be equal to. So at this point here, I can take f of 2 and I can substitute a 1 there. F prime of 2 gets substituted with a -3. So instead of saying plus f prime of 2, or instead of saying f plus f prime of 2, we'll say minus 3 and times x minus 2 to the first power. And then we go on to the next one. F double prime of 2 is going to be a 5. So 5 over 2 factorial is what we wind up with. So plus 5 over, and 2 factorial is just 2 times x minus 2 quantity squared. And then finally we're going to substitute the negative 7 for f triple prime of 2. So this will be minus 7 over, and 3 factorial will be a 6 times x minus 2 quantity cubed. And that is the third degree Taylor polynomial, where the f of 2 is 1, the first derivative is negative 3, second derivative is 5, and the third derivative is negative 7. And that's really all there is to it. Now, of course, if you don't know how to write this to begin with, if you don't have that first bit, then getting to the answer, of course, is going to be a bit of a challenge. So taking a look here at the second one, use the formula above, the Taylor polynomial formula that was basically given to us in the notes, to construct a Taylor polynomial that approximates f of x for sine of x, centered at 0, of degree 5. So because it's centered at 0, that's why we're going to call it a Maclaurin polynomial. So if you did the investigation, I'm going to kind of create a little table similar to what we did on the investigation with this. Because it's saying a degree 5, I'm going to say f of x is given us to be sine of x. F prime of x, the first derivative, will be cosine of x. The second derivative, in this case, will be negative sine of x. The third derivative, in this case, will be negative cosine of x. The fourth derivative is going to put us at sine of x. So now we're starting to repeat. And the fifth derivative of function f puts us back to cosine of x. And what we want to know is, what are the outputs here going to be? What is f of 0? Because that's where that's what our center is. That's what we're evaluating the function at, or that's what we want to be able to approximate sine of x for, is that x is equal to 0. So sine of 0 in this case is 0. Here, f prime of 0, cosine of 0 is going to be a 1. And then we're going to just keep going. The second derivative at 0 is going to be a 0. The third derivative at 0 is going to be a negative 1. The fourth derivative at 0 is going to be a 0. And the fifth derivative at 0 is going to go back to a positive 1. Now, by identifying where I have zeros, essentially, it kind of lets us know that, like the second derivative, the fourth derivative, the even number, or at the original one where I have like the 0th derivative, I guess you could think of it as. Essentially what we're going to be working with for our even numbered or our even valued derivatives, those are going to have a value of 0, so they don't really need to be included in the polynomial. But I'll go ahead and write them out just so that we understand. But let's go ahead and start writing our polynomial here. And so once again, I'm going to just kind of write out the generic formula. So I'm going to say to a 5th degree p of x, okay, we'll have f of c plus f prime of c times x minus c plus second derivative of c over 2 factorial times x minus c quantity squared plus third derivative of c over 3 factorial times x minus c cubed, and we're going to kind of have to keep continuing on the next row here, plus the fourth derivative at c over 4 factorial times x minus c quantity 4 to the fourth power, plus the fifth derivative of c over 5 factorial times x minus c to the fifth power. So that's what the generic one is going to look like. Okay? And again, some of you don't need to go through this whole generic one. You have it memorized and you say, okay, I know where the zeros are going to go, and you can just automatically omit them. Okay? But I'm trying to be thorough so that way the people that need to see it will see it. So f of c, meaning essentially, in this case, we're looking at 0, f of 0 in this case, is 0. And then at the first derivative, we got a 1. So I'm going to wind up with plus 1 times x minus 0. And of course, you don't need to write the 0, but again, I'm not trying to rush through it. This next one, we had 0 over 2 factorial times whatever, but because we have a 0 in the numerator, we're going to wind up with a 0 for our second derivative spot. For the third derivative, we had a negative 1, so let's change that sign to be a negative, because we're substituting a negative 1. So I'm going to get negative 1 over 3 factorial times x minus 0 cubed. The fourth derivative spot, again, is going to give me a 0 in the numerator of its fraction, so that becomes a 0. And to the fifth derivative spot, we're going to substitute a positive 1, so that'll be plus 1 over 5 factorial times x minus 0 to the fifth power. So of course the 0 terms don't matter, and when I substitute 0, or when I subtract 0 from x inside of the parentheses, really all we're going to have is an x. So 1 times x minus 0 is just going to be 1x. Negative 1 over 3 factorial is going to be a negative 1 over 6 x to the third power. The next one, 1 over 5 factorial, is going to be a positive 1 over 120 times x to the fifth power. Or if you prefer, you can write it as x minus x cubed, if I could write a cube, or get a 3, x cubed over 6 plus x to the fifth over 120. Okay? Now, this would be the fifth degree Taylor polynomial. This is where we're going for the solution of this particular problem. But one of the things that I want to illustrate with this one is, what would it be if we continued, if we just wanted to know it for any particular degree of polynomial? Okay? If I wanted to know it for any particular degree of polynomial, we're kind of looking at our pattern here, and we notice that all of the even valued degrees are going to be missing. And so I can look at it generally as x minus x cubed over 3 factorial plus we had x to the fifth over 5 factorial. And if we kept going, because we do have alternate, every other term, every other odd degree term is going to be negative. So the next one would be x to the 7th power over 7 factorial. We could kind of keep going with that. to where we have a negative term, a -1, raised to the power of n to show the alternating terms from positive to negative. And what we're doing to get the powers of x is I'm going to take whatever the I'm going to take whatever the nth term is, and I'm going to say multiply it by 2 and add 1, so that way we can get our odd valued exponents. And all of that is going to be over whatever, the same thing, the same expression that I had for the exponent spot. In this case, will be 2n plus 1 to give me those odd numbers in the denominator as a factorial. And the only reason I'm going to this is because this is going to be one of the types of Taylor polynomials that you're going to be expected to make sure that you can recognize it on site, that you have it memorized. So even though the polynomial, or even though the question itself only asks us to go to the 5th degree, which is what we did, we want to make sure that we can identify what the Taylor polynomial is going to be written in terms of a series, okay? And that's one of the things that we're heading towards with some of these examples. All right, so I would encourage you here to see if you can write an nth degree. This one is asking you not to go to a specific one. It's just asking you to go to an nth degree Maclaurin polynomial, meaning that it's centered at 0 of function f being equal to cosine of x. I encourage you to pause the video and try working it out and see what you're able to get. And let's go ahead and start taking a look at it. I'm going to work this one about pretty much the same way that I did on the last example. I'm going to start off with f of x being equal to cosine of x. The first derivative of x in this case is going to be negative sine of x. The second derivative of x, or the second derivative of the function, in this case the derivative of negative sine, will give me negative cosine of x. The third derivative gets me back to sine of x, positive. When I get to my fourth derivative, we're at cosine of x, so we're back to where we originally started at. And the fifth derivative gets me negative sine of x. And again, what we're going to notice here, we're going to have, again, alternating zeros for our outputs here. So let's just get another color for the outputs here. So f of 0, in this case, cosine of 0 is 1. F prime of 0, negative sine of 0 is 0. F double prime of 0, negative cosine of 0, in this case will give me a -1. Sine of 0 puts me back at 0. Cosine of 0 puts me back at 1. And negative sine of 0 is still 0. So in this case, what we're going to be looking at is we're going to have the initial term, and we're going to have the even degreed parts of the polynomial when we put it together. Okay? So let me clean this up because I'm going to want the space here, but I just wanted to illustrate that. So again, let's go ahead and write out what the generic Taylor polynomial would be. I did it through the 5th polynomial, but we're trying to establish a pattern. So I'm going to say p of n of x for any degree will be equal to f of c plus f prime of c times x minus c, or a if you prefer, plus second derivative of c, not x, over 2 factorial times x minus c quantity squared plus third derivative of c over 3 factorial times x minus c to the third power plus the fourth derivative of c over 4 factorial times x minus c to the fourth power plus the fifth derivative of f at c over 5 factorial times x minus c to the fifth power. Now really all that should be in one long horizontal segment, but I'm not having enough space here. Hopefully you have space on your paper to do that. So obviously the odd degreed parts are not going to be used. Okay, so here, moving on, substituting what we have, and this one I'm not going to include the 0 parts because I think the last example was enough to do that, and hopefully you're able to follow along and understand when we're going to, not include 0 because it's not necessary. So a Taylor polynomial for any degree for cosine of x, okay, we do use the first term. So I'm going to have a 1 here. We use the second term, which is negative. So I'm going to say minus 1 over 2 factorial times x, and x minus 0 is just going to be x squared. So minus, let's just say x squared. The next term that we get is going to be our fourth degree portion, which is going to be a positive 1 over 4 factorial times x to the fourth. And we don't, have it continuing, I only did it out to the fifth degree, but if I wanted to continue, the next one would be negative, and that would be 1 over 6 factorial times x to the sixth. I suppose if you prefer, you could write it as 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. And we can use that to kind of help us develop a pattern. And that's what we're asked to do. We're asked to write an nth degree, not a sixth degree or a fifth degree or anything like that. So in this case, we do have something alternating. So I'm going to say negative 1 to the power of n. So I have that gives me my alternating signs. The exponent values are all going to be even numbers. So I can take whatever the term number is and multiply it by, what do we have? 2. We can multiply it by 2. So the first term here is 2. So 2, or the 1 times 2 gives me an exponent of 2. This would be the the third term. So 2 times 3. Nope, the second term times 2 gives me exponent of 4. This is our third term that we're seeing. So 3 times 2 gives me 6. So I can take whatever the I can take whatever the term is, in this case x, and I can multiply it, or I can raise it to the power of 2 times n. And in the denominator, we're kind of seeing the same recognition. Whatever the first term is, we multiply it by 2 and we get 2 factorial. Whatever the second term is, we multiply it by 2 and we get 4 factorial, and so on. So here I'm going to say over 2n factorial. And this is what we get for a nth degreed Taylor polynomial expression to approximate to approximate cosine of x. And the last one that we're going to be looking at, if you notice again, at the kind of at the beginning of the lesson, I told you that there were going to be three that we kind of focused on: sine, cosine, and e to the x. Well, here's the e to the x one. So again, I encourage you to go ahead and see if you can pause the video and work this one out and see what you end up with. But let's go ahead and start working it out. So I'm going to work, same approach. F of x is going to be e to the x. F prime of x, the derivative of e to the x is e to the x. This derivative of e to the x, again, e to the x. So I think you can kind of see how this one's going to start playing out, e to the x. Okay. And we want to know what the values of those are going to be. And in this case, we're doing them at 0 still because it's a Maclaurin polynomial. So I'm going to say f of 0 here. And e to the 0 power, well, that's pretty easy. That's 1. All of these are going to have the same output because anything to the 0 power, besides infinity, obviously we're not worried about that one, is 1. Okay, so looking at the signs of the outputs, they're all positive, so we're not going to have any kind of alternating issue going on like we did with sine and cosine. We're not having any zeros, so it doesn't look like we're going to be skipping any degreed terms, so we're not skipping odd terms or even terms like we did with sine and cosine. So here, one more time, let's see, let's go ahead and write out the generic Taylor polynomial. So the generic Taylor polynomial, P of n, P sub n of x, f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c quantity squared plus f c over 3 factorial times x minus c to the third power plus, and we'll just keep going. I'm not going to finish writing all of them out here. So what do we get? F, let's see, P sub n of x. Well, f of c was a 1. F prime of c was a 1. And so if we say x minus 0, we're going to just wind up with 1 times x. So that would be plus 1x. Then we get another positive value. 1 over 2 factorial would be 1/2 times x. So that would be, or x squares, that'll be x squared over 2 factorial. And then we're going to wind up with the next one. 1 over 3 factorial times x minus 0 cubed would be x cubed over 3 factorial. And you can see that it's just going to kind of follow that pattern, x to the 4th power over 4 factorial plus x to the 5th power over 5 factorial, and so on. So in this case, the way that I would express a to the nth degree, I would just wind up saying x to the power of n over n factorial. Now, what it's telling you here in the next bit of our notes, it says your it's telling you you need to memorize the Maclaurin polynomials for those three functions, for cosine, sine, or for sine, cosine, and e to the x. Those are going to be things that you need to make sure that you can recognize them when you see them. So here in series form, in sigma notation, when we write it as a series, okay, let's pick another color here. So for sine of x, where n equals 1 to infinity, we had the alternating, oops, that's a 1, not an n. We had something alternating, so negative 1 to the power of n. And then here, because we were using the odd degreed portions, we said times x to the 2n plus 1 to ensure that we always got an odd expression. And in the bottom, we had 2n plus 1 factorial. So it alternates on odd numbers for sine of x. For cosine of x, let's choose a different color here, I guess. N equals 1 to infinity. And cosine was also alternating, so we had the negative 1 to the power of n. But in this case, because we were looking at the even degreed powers, we said x to the power of 2n, and it was over 2n factorial. And I guess technically that should be in parentheses, but if it's not, I think most people are going to recognize it's 2n factorial. And the third one that we had, that we just did, here, n equals 1 to infinity, we just wound up having x to the power of n over n factorial. And essentially all we were looking at here is they were increasing by like our counting numbers, the same numbers that we would use for a series anyway. And everything worked out to be positive. There was no alternating anything like that. And so those are our three Maclaurin polynomials for sine, cosine, and sigma, or sine, cosine, and e to the x in the form of a series. So make sure that you remember those when you see them. Now the next bit here is going to get into something that we're going to be using with a calculator. So I'm going to do my best to work with this stuff on a calculator because I'm still relatively new at working in Inspire. Here it's telling you to use a TI-89. Now I know for a long time TI-89s were kind of the workhorse of the calculus classroom, but I personally have never ever used a TI-89. I've always either used an 84 or an Inspire, and that's what I'm going to be looking at for this one. Now, pay attention to this bit here because this is a little bit innocuous. It's not really telling us, this is something that we. Oh, I want this. This is something that we need to know if we're using a Inspire calculator. And I guess it tells us the same thing for the 89 if you happen to have one. This is how we actually enter it into the calculator. We're going to say we want to do a Taylor series, and the expression here, this expression, this is just whatever your f of x happens to be. The variable is typically going to be x. The order or degree, that's what we're looking for. We're looking for the degree. Okay, so that would just be a number. Like if I wanted the fifth degree, I would say a 5. And if we're doing it, for whatever the center is, so when we type it on the calculator, it's going to look like that. Okay, although here where it says f of x, that you'd actually have whatever your expression is going to be. But that's how you would type it into the calculator in order for the Inspire to, it'll produce the Taylor polynomial that we would be working with. So use the Maclaurin polynomial, meaning a Taylor polynomial centered at 0 for f of x equals sine of x. This is going back to what we did from example 2. But here it's asking us to evaluate it for a 5th degree polynomial. So here, this is where I know this is going to be a 5th degree polynomial. And we want to evaluate it at 1.5. And we obviously didn't do 1.5 because that's not a standard value, standard number that we look at it on the unit circle. So this is how we're going to work this one out. And I'm going to go to the calculator here in just a moment to do it. But we're going to select the Taylor function on our calculator. So the display will say Taylor like that. Our function in this case is going to be sine of x. The variable that we're looking at, of course, is in terms of x. We are doing a 5th degree, and we're centering at 0. Now, if you don't enter the center, the calculator will presume it's going to be 0. So if you close the parentheses after the 5, it will work the same thing as if you actually type in the center of 0. Okay, so let's wish me luck here. Here's the calculator. Oh, and I need to come back here for a second to get off of my pen icon, because otherwise things aren't going to work the way that I want them to. Now, see, I believe it tells you in the instructions, it says to go to menu C4, so that's what I'm going to do. I'm going to go to menu, I'm going to go to 4 for calculus, and what it tells you to go to next is to C, so you can actually go up quicker to get to C. And we're looking at series. And for series, I want a Taylor polynomial. So 1 is highlighted, so I'm going to hit N. All right. So here, this is where I'm going to select my trig option, and I'm going to go sine of x, and I'm going to close the parentheses on the x. And then I'm going to hit my comma, and then we're evaluating in terms of x. And so I say comma, the degree of the polynomial that I want is a 5th degree polynomial. And we're centered at 0, so I'm going to say 0. And here I can either close the parentheses or I could just hit enter, because if I hit enter, the calculator understands that we're closing the parentheses, and we wind up with this. Now, if you remember, if you recall back to what I did when I worked this particular problem out the first time, I didn't leave the denominator in terms of a factorial. So 3 factorial gave you a 6, and 5 factorial gives you a 120. So those are the polynomials that we're going to be using. Now, what it's asking us to do, it's asking us to evaluate the function, what is p of 1.5. Now, I'm going to show you something here, and let me go back to this so you can write it down. I want to save that Taylor polynomial. Okay, I want to save the Taylor polynomial that we just got. So we know now that the Taylor polynomial, p sub 5 of x, was equal to x minus, what was it, x to the 3rd power over 6 plus x to the 5th power over 120. Now you can type in any number that you want to, obviously, but I think it's worthwhile, since we're talking about it. I did figure out how I can actually save that polynomial on my calculator. So what I'm going to do, this is what I'm going to type on the keypad. I'm going to, since we're using p for the Taylor polynomial, I'm going to hit the letter P, and I'm actually going to put it as p of x in parentheses like that. I'm going to hit p of x, or type it in on my display. Then the next thing I'm going to do is I'm going to hit the control button. Okay, after I hit the control button, I'm going to hit the template button. That's the one that kind of looks like the little book on your calculator. And when I type that, if I type that correctly into the calculator's display should look like this. It should say p of x and then it'll have it'll have a colon here with an equal sign. And what you're going to do at that, so this is what you should have when you type that in your calculator, and then you're going to just arrow up to copy your function. I'm going to just arrow up to grab that function again and put it there. Okay, so let me, again, cross your fingers, hopefully I got this all right. Okay, so we've been talking about function p, or the letter p to represent the Taylor polynomial. So I'm going to say p, oops, and I didn't go back to my pen, my pointer. That's why it's not doing that. Go back to my pointer so the whole computer knows I don't want to write anymore. All right, let's go back to there. So if I hit the P again, yeah, it had the thing there and it had the thing there. So that's doing it. Okay, so now we can say P of X, right? And then I'm going to hit my control button, and I'm going to hit my little, it's a little blurry on the screen, but it's the little one, I guess it was next to the book, the one right next to the 9. And I get the little colon with the equal sign. And so the calculator is going to say, okay, well, what function are we going to stick into P? So I'm going to arrow up, and I'm going to hit enter, and I'm going to grab that, okay? And once I hit enter again, there we go, it says done. So now now you guys probably could have typed it all into the calculator so much quicker than me trying to explain how you use the calculator to do this stuff. But now if I want to actually evaluate the function, what it says to do, evaluate the Taylor polynomial at 1.5, I can say P parentheses 1.5, and it'll substitute it for me. So I don't have to actually type in the whole polynomial for any value that I want to evaluate it for. So coming back to here, we're going to say, and let me kind of move this stuff out of the way a little bit. Move it over here some. Let's see, what is the value of, let me pick a different color. What is the value of f of, or p of 1.5? So p of 1.5 gave me 1, come on, I want to pick this is going to be equal to 1 point, and then what, 0, 0, 0, 78125. Thank you, calculator. Now what it's asking us to do, and I guess I'll just go ahead and erase this bit here because hopefully you have it. We need to write our answers here now. What is the value of f of 1.5? So here you just say sine of 1.5, and sine of 1.5 gives you 0.9974944,987. So that's what sine of 1.5 gives you. So the error in your approximation is going to be, and here it says recall the error is essentially the absolute value, because remember, if you were graphing these, you never know which one is going to be upper bound or lower bound. So we just take the absolute value to represent the distance that we would be, from one function to the other function on the y-axis. So we take the absolute value difference of whatever we have, because we never know which one's going to be bigger or smaller until we actually do the numbers. And when I do, the actual error here is 0.00328663. And I think that's a pretty good approximation, and that's really what Taylor polynomials allow us to do. It allows us to take a polynomial that we are so much more comfortable working with and get a really good approximation to what may be a very funky looking equation or function that we're evaluating, and it'll allow us to get really, really close enough to say, yeah, that's basically what the answer is going to be. So now it's asking us to find P of 2 and F of 2. So if I want to find P of 2 on my calculator, again, I'm going to just go here and I can say P of 2 and hit enter, and it gives me that 14/15. And otherwise, I can do it as a decimal number, 0.93 repeating. So let's go back to this. Let's get a different color here. So what did we have? This was 14/15, or as a decimal, it was 0.933 repeating. And if you say sine of 2 on your calculator, sine of 2 on your calculator will be 0.9092797,427. And if I take the difference between those two numbers, I get an error of 0.024035,907. So from the error that we had here to the error that we had here, you notice that the error is increasing. Why is the error increasing? Well, where was the polynomial centered at? We were centered at 0. So the further away that we go from 0, the more the error becomes, because it's an approximation. It's still an approximation. At the center, it's going to be dead on. It's going to be the same. But as we go, to the left of the 0, to the center, to the right of the 0, and the further that we go from in either direction from the 0, from the center, the less our polynomial is going to mirror or mimic the function that we're trying to approximate it with. And that could, be resolved by making a larger degree Taylor polynomial. We could, get a much better approximation by making the degree of the polynomial larger. But how does the error compare? Here, P2 of, P of 5 of 2 was greater than P5 of 1.5. One was bigger than the other one. What would happen if we worked it out to be 2.5? The error would simply get larger. The error will get larger the further you go from the center of the approximation, the more the error is going to get. Now, this next bit in your notes is talking about, it's introducing you to the concept of remainder, and we've seen remainders with our series information, where we would kind of say that the first unused term was the remainder, and that was good enough to get our error with from what the approximate value is going to be. And what we're going to see here with the error with the Taylor polynomial is really just kind of saying, hey, because we're talking about an approximation with the Taylor polynomial, there's going to be an error associated with it. Now, this particular lesson does not get into details very much on how you get the value of the error. That's going to come in a later lesson, okay? So right now it's just letting you know, because the Taylor polynomial is going to be an approximation, there's definitely going to be an error associated with it, okay? So let's understand that the exact value is going to be whatever your approximate value is plus your remainder, and that the error itself oftentimes, and here the error may kind of have the same kind of notation like this, where n is the degree, and sometimes it'll have both of these where the second number is where it's centered at. So here the error is going to be the actual value minus the approximate value, okay, as an absolute value. And we just did that. And here, I don't remember what this says. In order to use Taylor polynomials effectively, we use Taylor's theorem. And again, that's where we're really going to kind of get into things a little bit later on in a different lesson to estimate the size of the size of the error. The remainder given in the theorem is called the Lagrange form of the error, or the Lagrange error bound. And this gives us a bound for the error, but not the exact value for the error. So for now, think of the error as just the actual minus the approximation. So again, we'll get into more detail with the errors later on. And the last thing that it's kind of giving you here for the error stuff, if a function f is differentiable through an order n plus 1 on some interval where we have the number c, then for each x value in the interval, there must exist a number between x and z such that the Taylor polynomial exists. And what we're going to be getting at here, this is really where we're going to be identifying kind of the remainder information for a Taylor polynomial, where we're going to get into our error bound stuff. But for the time being, we're not really going to be doing anything with it. It's just kind of talking about it. This is referred to as the Lagrange error bound, or Taylor's theorem. And here they're saying that the remainder must be less than or equal to the maximum value of whatever you wound up getting for your Taylor polynomial over the n plus 1 factorial expression in the bottom, all of it multiplied by the difference of x minus c, where you get your center, the difference between x and your center, to the n plus 1 power. So we'll be looking at this a little in more detail later on. And here, yeah, there was where it's finally telling you that we'll see this stuff a little bit later. To be continued. Foreshadowing. All right. So there's two more examples that we're going to take a look at in the lesson, and they're really just kind of talking about, do you understand the behaviors of what a Taylor polynomial is going to be, and can you make some conclusions about a function using information from a Taylor polynomial? So here, given p of x, where it's second degree polynomial, that's what the subscript of 2 is equal to a plus bx plus cx, is a second degree Taylor polynomial for f about 0, so it's still centered at 0. What are the signs of a, b, and c if the function has a graph pictured in the right? I have no idea what that function is supposed to be. Maybe it's part of a, I don't know, what would that be? Maybe something got cut off for a exponential function? No, not exponential. Yeah, it could be, no, not so much exponential. Could be, yeah, decreasing exponential function, or maybe part of a rational function. I don't know. It's just a function. And all we want to know is, what are the signs? So can we identify whether A, B, and C, are they going to be positive? Are they going to be negative? What are they going to wind up being here? Let me get a brighter color. What are the signs of A, B, and C? Now, a lot of this is really going to be behavior. Not just behavior about a Taylor polynomial, but behaviors of functions in general. Remember, Taylor polynomial is made up of a bunch of derivatives of a polynomial at a certain degree. So here, we're going to be looking, because it's centered about 0, I can say this second degree polynomial at 0 would just be a, because if I just substitute 0 into the given function, these things go away, and I'm left with just a. Now, that value, and again, this isn't calculus based, this value, that is the constant, that is the y-intercept of whatever the second degree polynomial would happen to be. Now, the function itself sure doesn't look like a polynomial, but anyway, that's the y-intercept. Where's the y-intercept? It's below the x-axis, so that means a is negative. Or we can say that a is less than 0. Well, let's try to look at b. All right, let me pick a different color here for b. So let's look at b. Well, b, being where its position is, remember what the general Taylor form does. This is our first derivative. That's f prime of c. So here I'm looking at the first derivative. Okay. So if I take the first derivative there of the expression, here I'm just going to wind up with a b. Now, at x equals 0, okay, we're looking, think about it in terms of a derivative. At x equals 0, the function that we see at the right, is decreasing. Okay? So, if the first derivative is decreasing, then that tells me that the function itself must be below the x-axis. That's going back to things that we saw with our first derivative test. So, b is negative, or b is less than 0, depending on how you want to think about it. Okay, so now let's take a look at c. So remember, c, this is where we're getting into our second derivative. This is f double prime of c. So I'm going to evaluate it. What is p double prime of 0? Well, if I take the second derivative there, I'm going to wind up with either 2c, or I can think of it as p double prime of 0 over 2 is equal to c. And that's another thing that we did in our investigation that hopefully you understand why we're doing that. We just want to know what c is. Okay, well, what do we have here? Well, what are we doing it at? We're talking about it at x is equal to 0. Okay? At x is equal to 0, the function that we see is concave up. Because the function is concave up, the output at that point, no, it's not equal to 0. If it's concave up, then that means the output of the second derivative at that point is positive. And that's based on the second derivatives test. So that means c must be positive. Or you can say that c is greater than 0, whichever method that you prefer. So a and b are both negative. I determined that a was negative because, based on where it is, it's the y-intercept. The y-intercept is below the x-axis. It's negative. B is at x is equal to 0, the function is decreasing. You can clearly see it's going down left to right. So based on the first derivative test, the function must be negative at that point, making b negative. And the second derivative test is going to let us know that because the function itself is concave up, the second derivative test is going to let us know that c has to be a positive value. So that's how we're kind of looking at the behaviors of the function. Now again, this is a problem in all of mathematics. Students have a tendency to just have those blinders on, looking and saying, I'm just doing Taylor polynomials, just doing Taylor, how do I do it? How do I, you have a lot of tools in your, math tool bag. Don't just, think that everything can be fixed with a wrench when maybe a screwdriver or something simpler that you learned earlier on is going to be utilized as well. So here's our last example of things that we're going to be looking at. Suppose that the function f of x is approximated near x equals 3. So they're giving us something besides 0 as a center. They're giving us 3 as a center. By a third-degree Taylor polynomial, and they're giving us the third-degree Taylor polynomial. Huzzah! We don't have to figure it out. Okay, so find the values of f of 3, f prime of 3, double prime of 3, and triple prime of 3. All right, we can do this. Now, let's think about it in terms, again, of our general Taylor polynomial. Okay, so let's say p of x. Let's just go ahead and write it out one more time. We have f of c plus f prime of c times x minus 1, nope, x minus c, c to the first power, plus f double prime of c over 2 factorial multiplied by x minus c squared, plus f triple prime of c, golly, my hand doesn't want to work today, f triple prime of c over 3 factorial times x minus c quantity cubed. So that's as far as we need to go. Okay. Now f of 3 is probably the most straightforward one to get. This is stuff that you've been doing since your early days in mathematics. F of c, or I'm sorry, f of 3, we're going to just take it and plug it into the Taylor polynomial as it was given to us. So in this case, f of 3, all of the parentheses go to 0. So the only thing that's left is the 4, which kind of matches what that one was, right? That represents the original function when p of x is equal to f of x. So p of 3 must be equal to f of 3. Now, let's go on to, let's pick another color here. Let's try this lighter color. Let's try f prime of 3. Okay, so f prime of 3 represents the first degree position of the Taylor polynomial. And if you notice, that first degree position is missing. It's missing here. Okay, so if it's missing, then that means that f prime of 3 has to be 0. All right, so let's see, let's do black here, I guess. So let's try f double prime of 3. So let's get ourselves a little, take over some of this extra real estate here. F double prime of 3, in this case, is equal to the second degree portion of the polynomial, where we're looking at this bit here. Okay. Now, based on what we know for the second degree polynomial, all we're really concerned about is the number here, because obviously if I plug in a 0, to the parentheses, it goes to nothing. So I'm focused on the parentheses there, and I wind up getting, in this case, what did we have? F double prime of 3, if we were writing it out as a Taylor polynomial, is over 2 factorial. Okay? This is where we're at. This is what we're looking at. So in this case, it's equal to a negative 5. So if I want to know what F double prime of 3 is, I'm going to take the 2 factorial, and I'm going to multiply it on both sides, giving me negative 5 times 2 factorial, which would just be negative 10. And the last one that we have here, let's try and go with this. Let's do this color. I think that'll show up okay. So F triple prime of 3. So F triple prime of 3, this is the part that we're focusing on in order to be able to find out what that is, meaning that in this case, we're only really looking at that 6. Now, F triple prime of 3, according to the general form of the Taylor polynomial, is over a 3 factorial. And in this case, the Taylor polynomial gave us that value to be a 6. So, same thing like what I did for the second derivative. I'm going to multiply both sides by 3 factorial to get the third derivative by itself. So I have 6 times 3 factorial. Well, 3 factorial is 6. 6 times 6 is 36. Now, I would caution you against actually trying to find the first and second derivative, the first, second, and third derivatives of the polynomial itself, because they are going to be a bit misleading. Let's take a look at those. Let's just say, and so we're done. We have our answers. We got what we needed. Okay, this is just kind of a cautionary tale. If I were to take the first derivative of the function, if I were to take the first derivative of the Taylor polynomial, I am going to end up with a negative 10 times x minus 3 plus 18 times x minus 3 squared, if I'm just using, the power rule. All right? And if you tried to identify the first derivative off of this, so if we tried to go back to this part here, where I wanted to know the first derivative of 3, again, you're going to look like you're going to say, oh, I'm going to just substitute zeros in there, or substitute 3's in there, making all the terms 0. And you'll be like, hey, that's what I got, right? I got a 0. Okay, well, does that work for the second derivative? If I go to the second derivative of the Taylor polynomial, continuing on, I'm going to end up with a, so this is really just a constant, the way that we're looking at it, and we're going to end up with 36 times x minus 3 to the first power. Well, again, if I'm evaluating this particular second derivative at 3, you're going to look at it and say, well, the parentheses goes to 0, so the whole thing goes to 0, kind of like the first derivative did. But we know it's supposed to be a negative 10. Well, if you took that second derivative, the way that I have it written, and you wrote it out in standard form, 36x minus, and that would be what, 118, I believe it was, minus 118, I'll get an 8, and I forgot my x. I'll get a negative 10 when I do it that way. But this is why I'm kind of giving you a little bit of a cautionary tale here. Don't necessarily try to take the derivatives of the Taylor polynomial itself, rather than let's look at what the rule for the Taylor polynomial says the values should be at that point, especially since they gave us the Taylor polynomial. Okay? So the last bit here, does f have a local maximum, a local minimum, or neither at x is equal to 3? So again, thinking back, I know it's been a long time since you've had to think about local maxes and mins, but a local maximum occurs where the first derivative is going to be equal to 0. And I do have, in this instance, I do have a first derivative equaling 0. So there is a possibility that I have a local minimum, a local min or max there. Okay. Now, of course, it could just be a point of inflection, but let's see what we understand about it. All right. Here's my reasoning. At f prime of 3, we get 0. So we know there's a local extrema there. Now, if I go to the second derivative, f double prime of 3, we got a negative number, negative 10. Okay? Well, since that second derivative was less than 0, the function, according to the second derivatives test, must be concave down. So the first derivative test tells us that we do have an extrema at x is equal to 3, because the first derivative was equal to 0. The second derivative test is going to tell me that because the second derivative is negative at that point, the function is concave down, meaning that we have something like that. So based off of those two conclusions from the first and second derivative test, therefore I'm going to say x equals 3 is a local maximum. Okay? So we're at the end of the material, basically, for calculus, but we're having to make sure that we remember that information from so long ago. Okay. So just to recap, Taylor polynomials, make sure that you understand that it's 1, an approximation to a function. 2, how you identify the center of the Taylor polynomial. If the center is 0, we could refer to that as a Maclaurin polynomial. And we need to know the general form of a Taylor polynomial. There were 3 Maclaurin polynomials that we needed to make sure that we remembered in series form for sine of x, cosine of x, and e to the x. Make sure you have that information so that way you can recall it in your memory banks. And we also talked about how you looked at Taylor polynomials on an Inspire calculator. I know that there's a lot of information here, and I hope it was presented in a way that was understandable and easy for you to digest. But until next time, ladies and gentlemen, thank you for your time, and hope all is well in your world, and we'll talk to you soon.